Hi everyone, I'm Zhiming from Nanjing University. Today I will introduce you our recent work, Bernstein bounds for caustics. Caustics, the intricate patterns, are almost everywhere in our life. However, unbiased rendering of caustics are notoriously difficult. For example, when we use standard path tracing, we will find it hard for the passes to connect to the small light sources. It is because the incident radiance field at the ground shading point is a near data distribution, which is hard to sample or fit. So traditionally, we introduce some spatial relaxation like photo mapping. However, this usually leads to visible bias. Therefore, rendering sharp caustics is difficult because we always suffer from slow convergence, blurring, and noise. Since local sampling fails to reach a point light source, specialized methods connect endpoints with specular vertices. The problem is how to connect them. All we need is the position of specular vertices satisfying the reflection or Snell's laws. So we just need to solve the equations. However, this is already very difficult. There are two different lines of prior works: point sampling and region analysis. Point sampling usually starts from some initial guess and then refine it using some gradient-based iterations like Newton's method. Besides straight-line heuristics, we can also use uniform sampling or even importance sampling to generate these seed passes. But since Newton's method only has local convergence, point sampling usually suffers from visible outliers or magnetic convergence. So we consider deterministic search for specular passes, which means we select some triangle tuples first, and then we find solutions using Newton's method or polynomial solvers within each triangle tuple. Ideally, we want a faster selection process. At the same time, the size of the candidate set should be as small as possible. We motivate our method using two evident intuitions. Firstly, we notice that a triangle tuple's caustics are usually in a small region, which means we only need to consider each triangle tuple within a local region. Additionally, when the irradiance contribution of a specific triangle tuple is very low, we can sample it with a small probability without introducing evident noise. Indeed, this spirit emerged in previous works. However, something like in arithmetics ignore correlation between variables. Therefore, they produce very loose bounds. While methods based on point sampling are usually generic, they are not conservative and they still rely on the initial distribution, so they suffer from some outlier cases. Therefore, our key idea is to bound the position and irradiance range analytically. And later in the rendering phase, we use these bounds to drive stochastic sampling of triangle tuples. Again, a good bound should be both tight and fast to compute. To make this possible, we need to do a little bit more mathematics. Our method largely builds upon our prior work, Specular Polynomials, published at last year's SIGGRAPH. Here, UI represents the texture coordinates of I specular vertex. And we can model the relationship among three adjacent vertices using polynomial constraints and regional mappings. Now we already have a regional mapping, but how to bound it? To this end, we introduce Bernstein polynomial basis to rendering context. In particular, we can express a polynomial accurately using Bernstein basis. As we can see, the coefficients or the control points can cover the curve of this polynomial. And this property has been extended to rational functions, so we can use it to bound the range of any rational function. Now let's put everything together. We can just represent the caustics, or more accurately, the rational mappings with Bernstein polynomial basis to get their bounds. Here we show the rational functions as the blue curves, while the red dots represent their coefficients. We draw our computed bounds at the shaded blue regions. To improve tightness and handle singularities, we sometimes need to perform some domain subdivisions to compute the piecewise constant bounds. However, until now, it's still very difficult to handle the non-rational factors or high-degree components. Therefore, we regress these non-rational factors or high-degree components with low-degree polynomials plus a remainder variable to model the approximation error or uncertainty. Thus, the computed bounds are still valid and correct. But for irradiance, things will become a bit more complicated. To make this problem more tractable, we make some simplifying assumptions. First, we ignore the availability term and the first null term in the irradiance representations. When we expand the remaining Jacobians, we find the main part is the Jacobian between the first spectral vertex and the last receiver vertex. But how can we compute this Jacobian? Recall that we already have a regional modeling of the relationship between UK and U1. The derivative of a rational function is also a rational one, so the Jacobian is also a rational function. It's quite natural to compute the Jacobian using the explicit forward differentials, but sometimes we found the implicit differentials are better for refractive irradiance bounds. Also, we have to carefully design remainder variables to make sure both the primers and the differentials are properly bounded. Using our computed irradiance distribution bounds, we can write down the variance bound of a multi-sample estimator and optimize it to get the sampling probabilities. As a result, the variance of our optimized estimator is negligible, while standard importance sampling or uniform sampling suffers from visible noise or aliasing in equal time. For single scattering, our method also benefits from higher sample rates in equal time because we make the sampling process much faster than previous deterministic pipelines. In this sense, we make deterministic search of specular paths much more tractable. This speed difference is much more evident for double scattering. Here we acknowledge the test census are a bit simple, and also the pre-computation process takes about half of the rendering time, so the efficiency must be optimized in the future. Besides planar receivers, we also run methods on realistic census with more complex receivers. This animation also shows our method is temporally stable, thanks to our accurate modeling and extensive pre-computation. Recall that we use remainder variables to keep the bound valid when we do all kinds of approximations. This aligns with our theoretical focus. However, when we remove these remainder variables, we found the violation is so small. Anyway, any invalid irradiance bounds only leads to higher variance instead of bias or energy loss. So we believe there is still a huge space for performance optimizations. Nevertheless, the main limitation is still the number of bounds. We believe the single scattering bound is already good, and the double scattering is also useful in many cases, but triple scattering is tough even for our toy cases. Also, we made some simplifying assumptions in our derivations. As a brief summary, our method builds upon the best practice of region analysis. At the same time, we also benefit from stochastic sampling, just like manifold path guiding. The elegant properties of Bernstein polynomials lead to our comprehensive bounds for caustics. And we also hope we can inspire future works to develop some improved bounds for caustics and beyond. Thanks for listening.